All right.
Are you still on the wall?
Yo,
Oh,
y'all don't fling the pillows about like you're in elementary school or something. Y'all can do better. Okay, let me do, I'm sorry, baby. I'm sorry. Let me turn this one on. That's my good boy. That's right. That's right. You're my good boy. Okay. He's a good fella. He's a good fella. Yeah, he is. He's such a good boy. Ta-da-da-da. And we are in. There we go. Down. Stay participant. Got it. No audio. Flip camera. There you go. All right.
like we never talked about what happened.
All right. Is everyone happy they brought a drink? Yeah.
I'm like walking up and down. It's a lot.
That was nothing.
You dad.
Y'all are crazy people.
All right, my friend Jack, you guys did a couple of crazy people. All right, so everybody seems surprised that we've gone as far as up around the bend, right? So we're not writing that one down. We're just keeping it in our binder because it was fun. Now, next week's lab. Okay, next week's lab is going to require a device that you can put an app on. Okay, and your phone's going to be easiest.
I don't think I'll be able to do that.
We'll be able to do it. You can borrow, you can work with somebody else if you need to for that. And I recommend once you have that app, you keep it because it kind of gets addictive. There are times when you'll be out at night and you'll be able to take this app, take your phone, point it at the sky, and it'll tell you what you're looking at. It's Skywalk.
Oh, I think my dad has.
Mhm.
We could have different planets or like something else in the atmosphere. They could still
Yep.
light out.
Well, it'll tell you now. And I had a student a couple years back who went to Africa on a vacation. And they were out in the middle of an African savanna where it was super dark looking up at the sky. And her tour group was like, I wonder what this is. And she's like, well, let me tell you, and brought her phone out and they were all shocked. They were all like, oh my gosh, that is the coolest thing. So yeah.
Oh yeah, I love.
Yep. So Yusuf, this is Yusuf's last day, by the way. So be sure you say have a good summer to him. Because Yusuf is leaving next Monday for India. How long are you gonna go?
Well, I hope I come.
He's not excited about the heat, but he's gonna be gone for a while. So he's gonna miss the end of our year, but
It's not that much better.
he's already caught up. So we're good to go. All right.
I ignore.
All right. So now that everybody's in and we're all chill, it's not gonna be hot in here, right? Maybe a little bit. Bring it down a hair just because. Okay, so let's start today. So today's lesson is on our solar system and stars. And we've only got one more actual lesson, right? And then we have review and then we're out of here. So let's see. Whoop, that went too fast. So this is what I was just saying to you. Before you get started, realize that we've got to have an app for next week. You're going to need to put it on a device that you're going to bring, and you're going to want to install before you get here, because for some of you, depending on whether you're Apple or Android, there may be a cost. I don't think it's more than $3. So it was $5 for you. Do you have an Apple or Android? Apple. Android. Okay, yeah, I thought it was Android that was more expensive for whatever reason. I don't know why.
$3 and
Oh, yeah, if you want to go without ads, it's $5, but to install it was $6.
satellite.
Yeah, then you add more. Yeah, but you don't need that necessarily. I do, if you really enjoy it though, upgrade it because it will give you alerts as to when there's going to be like a satellite pass that you'll be able to see. Or for example, it will tell you like when ISS is going to come overhead and you can go outside and watch the International Space Station come by. So for this app, there are links for both Apple and Android in your weekly email and in the lab in Teacher Ease. So if you open that assignment, there are links there, or if you go to read your weekly email, there will be links there as well. One more thing about this time of year, you have to keep up, right? If you get behind now, it's gonna be a problem. It's gonna be a real problem. So everybody has picked a topic for their research. Be sure that you research it thoroughly. Some of you have fictional places. You're gonna have to, that's gonna be hard for you to get geographical information, but you're gonna have to find like a real place where that place exists. You know what I mean? Like if you were doing Mr. Rogers' house, you're gonna have to decide where that is and give me actual facts about that area. All right, so I said Mr. Rogers, that y'all don't even know who he is, do you? Okay, good, because he's like the best. He's the best. All right, so here we go. This is your app, Star Walk 2. It'll look like this, all right? And it's Vito technology. Amazing. Once you have it, you'll get addicted to it. I used it just the other night. So our solar system, here we go. Yes, Drew. Mhm. Yeah,
And what's it called?
Rose.
Fly and you see the stars.
Yeah,
That's the wrong fly.
it's the wrong sky. Yeah. Oh, well, there you go. Mhm.
Exactly.
So formation of the solar system. Do we remember the difference between, what's a theory? What's a scientific theory? Jack,
Scientific theory is why.
why something, yeah, it's an explanation. Yeah. So we know the what here. The what is that the solar system exists. The why and the how in this case. These are our theories that we're going to come upon. And these are they're going to be all kinds of different theories of formation because we weren't here, right? We don't know. So it's at best an educated guess or a theory of some kind. Okay, so keeping that in mind, what do you call theories of origin? Jack? Formation theories, that's what we were just saying. All right, so formation theories are theories of origin of the solar system. There are lots of them, right? But there's mainly like one big scientific grand idea and then little ideas within the big idea. So a collapse of something, an interstellar what? Chloe? Yeah, okay. Now you get to the question, how'd the cloud get here? Oh boy, now we're just going to keep going. We'll just go back in time forever, right? And then you get issues of when does time begin? I mean, this gets, if you get involved in physics, especially the space sort of oriented physics.
Astrophysics.
Yep, all the astrophysics. It is as much philosophical as it is science, really. All right, so stars form when particles of space dust eventually concentrate together due to gravity and causes a cloud to collapse. So a collapse accelerates as the center, what happens? Caitlin?
As it becomes denser.
As it becomes denser. Yep, sorry, I clicked that one. The rotation speed is going to increase. What's this called, this process, when you've got something rotating and the center becomes denser and denser and denser? Yusuf, what's it called? Do you know? Well, that's the force. Yep, centripetal force. But what's it called? Bailey? Gravitational contraction. There you are. You're there. Yep, you had it. Not fusion, right? We had this whole discussion about it. I would definitely know the definition of gravitational contraction for your fun room. I would definitely know that. So, yes, sir.
But I think if the cloud collapses, I just bet you the Hoover noise in the background, just vacuum cleaner.
Okay, so matter what am I looking for here? These are molecules fused. What do I have, Piper?
Fusion?
So yeah, matter condenses, and that's when you get pressure at the center. All right, so you get, there you go. So you got your matter condensing because it's coming denser and denser, and you get pressure at the center, and when it becomes high enough, hydrogen and helium form the sun, right? And then you get temperature ranges from hot to cold, from the center to the outer edge. These are all the theories we're trying to figure out. Now, we do know that the sun is composed mostly of hydrogen and helium, and those things are cycling in a fission fusion sort of situation. So this is our best guess. So after this cloud collapses, we have what we call planetesimals, and they're formed by things that collide. What are they, Alex?
Particles.
Yeah, you got particles colliding. It's real easy there. So you got particles that are colliding and they form these planetesimals. So basically planetesimals is their way of saying like little starter planets, little baby planet, little starter planets. So your gas giants form. So what was the first planet to form? It grew by collecting planetesimals and material rotating about gas giants. What's the first planet, Jack? All right, so we're thinking Jupiter was the first to form. It's pretty big, right? Compared to all the others. All right, so it's going to grow by collecting planetesimals and material rotating about gas giants formed either what or satellites? Chloe. Yeah, either click. Why did that not go? Hello, that was not in order. The rings or satellite. There you go. So rings are like on Saturn and Uranus, right? We have rings. And basically, you've got all of this stuff flowing around the outside. What is meant here by satellites? What do we mean, Drew?
There's also a satellite. And then-
Correct. No. Huh. That's interesting. Okay, yeah. Moons, yeah, exactly. Anything that orbits is a satellite. So we have a satellite, a natural satellite. That's the moon. And then we have a gazillion that we've thrown up there. What's the big project right now to get satellites to cover the whole Earth with internet, satellite-based internet?
Something
Drew?
from
Starlink. Who's doing Starlink?
Musk.
Musk. Gosh, Musk is just ruling the world these days. So when they launch these satellites for Starlink, because the idea is there's very remote places on Earth where they don't have internet. And the idea is to be able to cover the whole planet with internet access using satellites. When they launch these, they put them up on a rocket and they're all in a row. So keep your eyes open for news that they call it a Starlink satellite train. And when they launch them, if you've not gone and seen it personally, it's wild. I've seen 3 of them now, I think, but you can stand outside at night and they have panels on them that will reflect the sunlight. So you can see them like little lights, and there is a little trail and they're perfectly spaced and they're all moving at exactly the same rate. And it looks like something, I mean, like a space invasion. Yeah, it's like a space invasion. They all come, and depending on what day it is, how close to launch, they're closer together or they're further apart. It's very cool. So your planetesimals are going to form your protoplanets. There's a root there. Proto is like what? What's proto, Alex?
Like new or not formed yet, or like baby
Yeah.
type. Like
Yeah.
precursor.
Precursor is a great word. Protoplanets. Yeah, not quite.
Proto dudes.
So you've got terrestrial planets. These are our inner planets, and they're formed by merging of planetesimals. Elements resist vaporization. They're rocky, they're dense, they're not like our gas giants on the outside. And then you have leftover debris. And this stuff diminished, collided with planets, left the solar system, or became what? What's in our solar system that's leftover stuff? James. There you go. All right. Anybody ever played the old game, the old 1980s game, Asteroid? Yeah, fun stuff. If you haven't done it, you should. All right, so this is what we call the nebular hypothesis. I got a lot of little videos today, mostly short, but covers everything pretty well.
Formation of the planets. The universe comprises countless galaxies, each one containing numerous stars. Around some of those stars, there are planets, just like those that orbit our own star, the Sun. The nebular hypothesis is the most widely accepted explanation for how the Sun and planets in the solar system may have formed. One, when our solar system was first created, all that was thought to have existed was a cold, spinning cloud of gas called the solar nebula. The nebula resulted from an uneven distribution of gases throughout the universe. As the gravitational pull began to condense the gas toward the center, the speed of the rotation increased. This caused the cloud to flatten, creating an accretion disk. Matter continued to collect as the growing force of gravity drew it toward the center. Eventually, the gas formed from the increasing pressure. As the mass further increased, the gravity also increased, and as a result, the temperature continued to rise. A ball of hot gas formed in the center of the accretion disk, creating a protostar, also known as the sun. Finally, when enough gas gathered in the center of the protostar, the pressure generated enough heat to fuse the atoms, forming a star. Outside of the star, matter was forming into clumps of gas, dust, and rock, which created protoplanets. These protoplanets continued to grow as they trapped material in their gravitational fields. Because the protoplanets all formed from the same cloud of gas at the top, they traveled around the sun in the same direction and in the same plane. The nebular hypothesis also explains how the planets are arranged. The heat and solar winds caused by the sun swept the lighter gases farther out into the developing solar system. This is why the rocky terrestrial planets, Mercury, Venus, Earth, and Mars, are located closer to the sun. The gas giants, Jupiter, Saturn, Uranus, and Neptune, formed in the cooler outer region of the solar system. The solar system continued to evolve even after its initial formation. Large asteroids slammed into planets, and the planets themselves differentiated into layers as they slowly cooled. Although the nebular hypothesis cannot be directly tested, it is a useful description for how a solar system forms. It explains why planets and the star they orbit usually spin in the same direction and lie in the same plane. It also explains the arrangement of the planets, with the rocky planets nearest to the sun and the gas giants farther away. The next time that you look at the stars twinkling in the night sky, imagine new planets forming using these very steps.
So we have a hypothesis. Can't test it, can we? So it's kind of weird because we always say a hypothesis is an idea that can be tested, but in this case, this one, it's kind of impossible for us to test given our current physical situation. Yes, Drew?
We had a spinning disk of gas. What if centrifugal force pull all the gas to the edges? Not to the
It would pull the denser molecules eventually because you get gravitational contraction, right? So everything, yeah, at beginning, yes, it's going to push it out. But there's a point, it's like if we had an office chair right here, and everybody ever done the thing where you sit in an office chair and you spin it and then you tuck yourself in and you spin faster and faster and faster? Mm-hmm.
You're on your muscles.
Right. Mm-hmm.
So, did it like this, arms would spread out.
Right, that will slow you down. But as you get denser towards the center, it spins faster, which continues to make things denser towards the center. We can look at it more later. So what do we call this backward motion of a planet, Chloe? That's right, retrograde. Now you'll hear these, you ever hear the astrologists be like, oh, Mercury is in retrograde, it's gonna be a bad day or whatever. They like that word, all right? So retrograde is this backward motion of a planet. And it inspired the search for better understanding of planetary motion and the move from a what model? How did we start? What was the first model of the solar system, Alex?
Geocentric.
Okay, geocentric is right. And what's that mean, everybody?
Around the Earth.
Earth at the middle. And our current model is what?
Helium.
Go ahead. Heliocentric, which is the sun at the center. And that was our buddy Copernicus, right?
Sun-filled jelly donut.
A what?
Sun-filled jelly donut.
Sun-filled jelly donut. Okay, all right. So we got our first scientist here. There's a couple we're going to talk about here, and we're gonna watch little short videos on them too, because these are some very interesting, influential guys. So first we had Copernicus, and Copernicus is like, yo, everything is not revolving around the Earth. We're actually revolving around the sun. And we'll talk about kind of how we got into that. And then we have Kepler. Okay, so Kepler, this is a much more modern scientist. And he talked about how the planets are orbiting in an elliptical pattern, not a circle, but an elliptical pattern. Bailey,
Oh, yeah.
you're gonna do ellipse? What's ellipse? It's an oval shape. Okay. You've seen with Earth, when we've talked about Earth, like last week, we talked about Earth's elliptical orbit around the sun. And our moon has an elliptical orbit around Earth, right? There are times when our moon is farther away, times when our moon is closer. What happens if you're near water? What happens when the moon is closer to you? What do you get, James? You get a higher tide, right? And that's because the moon, the gravity of the moon is actually affecting the water on Earth, and it's pulling it. So if you've got a big full moon overhead and the moon's real close, you're going to get this tide situation. All right, so you got this oval shape. That's our elliptical orbit. And it's so far, as you learned today, that we measure things in astronomical units. Does anybody know what that number is right there? Jack, what is it? 1.496 times 10 to the 8th kilometer. That's what we use as our AU. That's our astronomical unit. And that is a much easier way to go about giving the actual distance. Now, today we scaled the distance down, right? We really scaled it down. What was our furthest? Neptune was how far? Do you remember, Lily? You did Neptune. How far was it?
Was 600.
620 meters from the sun. We walked 620 meters. So if you were doing that in real units, those numbers are massive, right? You guys saw them up there before you did the scaling. So that's how we measure. Now, that should say ratio of distance between foci to length of major axis. I'll just tip this one up for you. So this is the eccentricity. These right here, I don't need you to like worry too much about them. Just know they exist, okay? Now, do know a bit about Kepler's laws. So this is Kepler's first law, that planets are going to orbit in an elliptical pattern. So which law is going to talk about planets moving faster when they're closer? Yusuf? That'd be second. Yep. Oh, and I bet you can guess this one.
Fourth.
Yeah, fourth. There, Sky, what's this one going to be? Third. Yeah, Kepler's third law. Okay, so think about it. They move faster when they're closer to the sun. Why would that be a thing? Bailey. What's going on as it's passing the sun, Drew?
Well, but it was like the journal used, when you get closer, you're getting faster.
They're getting closer and closer. Yusuf, you want to add something? Yes, centripetal force again. So they're getting closer and closer to the sun. And as they're passing it, that they're going to speed up because that gravity is affecting it. You know, when we send satellites and stuff, sometimes we use a slingshot effect. Have you guys heard that? Yeah, sometimes we will launch stuff intentionally. Yeah, well, usually the moon because it's close. Well, we use the moon's gravity to kind of fling whatever it is we're trying to send up. So in his third law here, it talks about an orbital period is the length of time it takes for a planet to make a complete orbit around the sun. And it's the relationship between the orbital period and the size of an ellipse. And it's a little formula that looks like so. Yeah. So who was the first person to use a telescope to discover Jupiter's 4 moons? All right, Liam. Galileo. Figaro. Okay, Galileo, cool dude, super cool dude. All right, so he discovered Jupiter's 4 moons, and he proved that not all celestial bodies are orbiting Earth because apparently those things are orbiting the moon, not Earth. I mean, orbiting Jupiter. Those moons are orbiting Jupiter. So he's the one that was like, hello, world, we're not the center of the universe, although we think we are. There's your Galileo, just like you wanted. See, I delivered. Yes, who had a question? No. Okay. All right. So here's Kepler's laws with a little animation to make them a little clearer than their big, long, wordy definitions.
Hello, learners. This is Steve Engineering. Today, we're going to talk about another fun topic in physics. It's all about the Kepler's laws of planetary motion. Kepler's laws of planetary motion are laws describing the motions of the planets in the solar system. They were derived by the German astronomer Johannes Kepler. There are three laws of planetary motion. Let's talk about them one by one. Kepler's first law of planetary motion, sometimes referred to as the laws of ellipsis, can be stated as all planets move about the sun in elliptical orbits, having the sun as one of the foci. This means that planets are orbiting the sun in a path described as an ellipse. This is a picture of an ellipse. Suppose this ellipse is where the planet Earth moves. The Earth moves along the ellipse around the sun. The sun is located at either one of foci of the ellipse. Now let us move on to the second law. Kepler's second law of planetary motion, sometimes referred to as the law of equal areas, can be stated as a radius vector joining in the planet to the sun sweeps out equal areas in equal lengths of time. The second law describes the speed at which any given planet will move while orbiting the sun. Know that when a planet is close to the sun, it moves fast, but when a planet is far from the sun, it moves slowly. So if we draw an imaginary line of the movement of the planet and the sun for every month of the year, we can see that when the planet is close to the sun, it will form a wide but short triangle. And when the planet is far from the sun, it will form a thin but long triangle. The Earth would have to adjust its movements in order to match the imaginary area. Did you know that the knowledge of Kepler's second law is proved the importance of Newton's law of gravitation? Newton showed that the motion of bodies subject to central gravitational force doesn't always follow the elliptical orbits as specified by the first law of Kepler, but instead, planets or other heavenly bodies can take paths defined by other open conic curves. Amazing, right? Now let us move on to the Kepler's planetary motion, sometimes referred to as the law of harmonies, can be stated as the squares of the sidereal periods of the planets are directly proportional to the cubes of their mean distances from the sun. It compares the orbital period and radius of orbit of a planet to those of other planets. It is the ratio of the squares of the periods to the cubes of their average distances from the sun is the same for every one of the planets. The comparison of each planet can be shown in this illustration. Now, what does that mean? Kepler's third law means how long a planet takes to go around the sun, which is its period, is related to the planet's mean distance from the sun. That is, the square of the period divided by the cube of the mean distance is equal to a constant. And for every planet, no matter what its period or distance, p squared over r cubed is the same number. And that's it. Did you enjoy our topic for today? I hope you certainly did. See you again next time for more interesting and fun topics only here in.
So mathy math again, more mathy math. If you like physics, especially astrophysics, like we're saying, it's a great direction to go. All the mathy math, if you love the mathy math. So gravity is the attractive force between two objects. Is there gravity between Piper and Caitlin?
Yes,
Yeah, is there a gravity between Piper and the couch?
yeah,
Why is Piper stuck to the couch and not Caitlin?
because Caitlin has a rather small mass compared to the entire weight of the earth.
That's a good way to put it. Yeah, Caitlin's mass is far less than that of the Earth. So the reason Piper is not sucked over to Caitlin is because the gravity between Piper and the Earth, which is the Earth is attracting the house, right? Pulling the house and pulling the couch
Your
and then
house.
pulling Piper. Yep. But there is gravity between Piper and Caitlin. I'll see if we can find it for you because I don't think I included it, but there's a great video. This guy takes like a stretchy, almost like a bathing suit material, and he puts it over a big hoop. Y'all good? And he sends like little marbles, rolls them out on it. And they roll around and roll around and roll around. And as they get close to each other, they just they come right together. You can actually see it in action. It's pretty neat. So yeah, there's gravity between any two objects. So now we have another guy. Now we have Newton. Newton has this universal law of gravitation. And it states that this is an easy one, Chloe? Yeah, every particle, every object, everything, right, is going to attract every other particle, every other object, every other thing in the universe with Alex?
Force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their sides.
Yeah, now we could put the word directly here. That would be more specific, but it implies, unless you're putting inversely. What is an example, somebody, of something that is directly proportional? Think for a minute. Something that's directly proportional. No? Anything, an example of anything that's directly proportional. Yusuf. Erosion, well, it depends on what kind of erosion. Because like, remember, rocks and stuff, they erode more when it's cold out versus when it's warm. Alex, what's your example?
Not like the inverse. Okay, so the normal would be.
Direct, just give me direct, directly proportional.
As pressure increases, temperature increases.
That's a good one. The more I eat, finish it. The more I eat,
The more children.
the fatter I get, right? These are all directly proportional, right? Okay. Oh, okay. What is,
The more bodies you have to hide.
right? Well, that's a good one too. That would be like the more people I murder, the more bodies I have to hide, right? Okay. What is something inversely proportional?
I got one for this one.
I'm sure you do. You may be able to think of a non-sciencey one too. Just think about it. Alex, what's your example?
The higher you go in the atmosphere, the colder it gets.
That's a good one.
Well,
Well, that's, well,
Actually, higher you go, the lower the pressure gets.
yes, as you increase your altitude, your atmospheric pressure will decrease. That is correct. That would be inversely proportional. Anybody else have another example? Nope. Okay, we get the idea. We remember these, right? Okay, so gravity and orbits. So who discovered that gravity explains why planets move? Yusuf. Yeah, Newton. Here's our guy, Newton. Love Newton.
It's named after him.
Where would you find Newton today? Correct.
6 feet under.
Correct. Where is he?
Under.
Where is he?
Somewhere in England.
He's not 6 feet underground.
Oh.
In space.
Nope.
He's buried.
James,
In the museum?
Oh, it's in the water.
he's in a crypt. Where is he?
That might be 6 feet under the ground. Wait, no.
He's in Westminster Abbey.
Let's see.
Is he in the water?
No, he's in Westminster Abbey
He's
In
not
London.
water.
in a church. Yep, he is very dead, but yes, he's in Westminster Abbey. Okay, so the center of what is the point between a planet and a sun, or just above the sun's surface, that's actually orbited? Center of Yusuf? Center of mass. Okay, this is one of these ones. You can do center of mass experiments with people's bodies. Have you seen these? Adult men and adult women have a different center of mass. Have you ever seen this? Yeah. If you want to see funny videos, you can look up what now? Yeah, you can look up center of mass men and women, and there's some of them are really funny. Like there are some things that, like, just positions you can get your body in that, like, for example, maybe a woman could just stand right up, but a man can't stand right up because the weight is in a different place. The center of the mass is in a different place. I saw one recently, and I don't know if it's actually true, but this woman put like a broomstick behind her arms like this, like so through her arms. And then she got down and she put her face on the floor, and then she got back up, and her husband was like, okay. And he tried to slap his face on the floor. I don't know if that one's actually true, but it was funny. Drew.
Okay, there are certain still rings that are just impossible.
Yeah, because the center of gravity is going to be very different. All right, so here's our buddy. Let's have a look at our friend here with gravitational force.
Gravitational force acts between any two objects in the universe. One easy way to demonstrate the effect of gravitational force is to suspend a horizontal scale with two masses at the end, as shown. Now, quickly place two large masses next to the mass of the scale. If you wait and observe, you can see the two small masses will move closer to the big mass, and eventually they will stick together. This force of attraction happens due to the gravitational force. It looks interesting, right? Let's learn a few more details about the universal law of gravitation and how Sir Isaac Newton discovered this very important law. As we all know the story, an apple fell down from a tree, which started Newton thinking. Let's assume there is one more apple tree that is far away from the current tree, and an apple falls from it as well, as shown. If you analyze this way, it is clear that objects fall to the earth in a radial direction, or the earth attracts the objects radially towards the center. This observation was the turning point in the discovery of the universal law of gravitation. Newton realized that the earth does not attract the objects just down, but it attracts the objects radially towards its center.
Parker,
It's
can you
logical
see?
to conclude that in a
Sure you
similar
can
way,
see.
the earth is pulling the moon radially towards its center with an attractive force. Similarly, the sun as well is attracting the earth towards its center with a certain force. Now let's move away from these rounded objects. With the same logic, this car will attract this towards its center of mass. Similarly, this book will attract this car towards its center of mass with a certain force. According to Newton's third law of motion, these two force values should be equal. In short, all the objects in the universe attract each other with a certain force. This is the universal law of gravitation. Now, the next challenge. Newton wanted to derive an equation to predict the magnitude of the force which arises due to the universal law of gravitation. Newton's intuition told him that the effect of gravitational force would dilute with distance, but to what extent? To get an answer for this question, he looked at the moon. The moon is also attracted to the earth due to the same gravitational force. However, the moon doesn't fall to the earth because the centripetal force required for the moon's circular motion is supplied by the gravitational force. People at that time already knew the moon's angular speed and the distance between the earth to moon. Based on this force balance idea, Newton calculated the centripetal acceleration of the moon. The force acting on the apple near to the Earth's surface can be easily calculated by measuring the apple's acceleration. The value of this acceleration is 9.81 meters per second squared. Newton compared these two acceleration values with the distances from the center of Earth. Can you spot any connection between these four numbers? If so, congratulations. Anyway, Newton was able to find out a definite connection between these four numbers. Divide the acceleration values. Now, I'll take the square of the distances and divide. Surprise! The resultant values are very close. This means the gravitational force is inversely proportional to the square of the distance between the center of the objects. What a brilliant deduction.
Brilliant.
The next question is, do the objects' respective masses have any connection with gravitational force between them? Newton had already derived the equation for an object's acceleration during this period, and it is a common observation that when the force arises due to gravity, the value of acceleration does not change.
I wanna
based
know
on
where he
an
got
object's
pineapple.
mass.
In London.
Therefore, the
got
value of
pineapple.
force due to the universal law of gravitation should be a factor of the mass, so that when you find out the acceleration by dividing the mass factor will get canceled. Likewise, we have to include the mass of the second object as well in this equation, in this case, the Earth's mass. This is the expression Newton derived to find out the force due to the universal law of gravitation. He introduced a constant called the gravitational constant and made it a proper equation. According to the universal law of gravitation, all the objects in this universe attract each other. In this case, The Earth attracts the apple with a force value defined by this equation. The apple also attracts the Earth with the same force value. However, the Earth doesn't move to the apple because when you divide this force by the mass of the Earth, the acceleration value becomes negligible. The case is the same with every other object in the universe. It's somewhat impossible to believe, right? Are all the objects in the universe really attracting each other? We find this idea difficult to believe because we live in a world where frictional force is always present. Just imagine a long frictionless room with no object in it. Now, introduce two blocks on the floor. If the frictional force between the object and floor is zero, you would see the blocks move toward each other due to the gravitational force and finally collide. Of course, this was a hypothetical experiment. A more realistic experiment to visualize the effect of gravitational force would be placing two heavy balls near a hanging two-ball arrangement. If no objects are near them, you'd observe that slowly the small balls would move to touch the larger ones. Even though Sir Isaac Newton derived the equation for the universal law of gravitation, he didn't find out the value of G. Many years later, an English scientist named Henry Cavendish came up with a clever idea to determine the value of G. His experiment was very similar to the example we saw earlier. The only difference is that his setup was able to attain a balanced force between the force due to gravity and the string's torsional force. You can see clearly that when the torque produced by torsion of the spring is the same as the torque due to the gravitational attraction force, the balls balance. Using this twisted angle at the balance as an input, Cavendish calculated the value of G for the first time. That too, quite accurately. We hope you now have a clear understanding about the universal law of gravitation. See you.
That Cavendish guy is a mather, right? But we did G last week, right? We had G in the homework. Yeah, that's how we get G. It's one of those things. It's good to, when you see those equations that are always, you can always use them, you can always plug them in. It's good to know where they came from, just so you kind of have an understanding. I asked, so in my, I think it was pre-algebra class, we had a student teacher that year whose name was Ms. Prizborowski, and God bless her, we had two boys in that class that ran her crazy. One of them's a preacher now. It's kind of funny because he was a bad little kid. He was a little mischief maker, but they made her nuts. And so she was always on edge. And we started using the number pi. And I wanted to know what pi was. And she told me, and I said, no, I know, but you can't just pull a number out of thin air and plug it in and it works. Like, what is it? And she couldn't explain to me what it was, but like, she didn't, I guess she thought I was trying to trick her and ask her something hard. She ended up crying. I'm like, please don't cry. I'm just curious. Like she would get, poor woman, I'm telling you, those boys abused her. So these three scientists that we've talked about so far, these are very short, quick little videos that explain who these guys are, which is important because most of what we do with science, physics, and astrophysics are these guys right here. Keep the dates in mind. That gives you some context, right? Yeah.
Italian-born Galileo Galilei was an astronomer, physicist, mathematician, and philosopher whose work changed the way that society viewed nature's laws and origins, thus contributing to the scientific revolution. Early on, Galileo expressed interest in entering the
Priesthood was the word there.
After leaving the University of Pisa before graduating, Galileo began tutoring mathematics full-time. He was given a 3-year tenure at the University of Pisa. He moved to the University of Padua in 1592, where he taught geometry, mechanics, and astronomy. Late in the 16th century, Galileo developed a geometric and military compass, used by surveyors and gunners. Galileo constructed a thermometer comprised of a sealed glass cylinder containing a number of objects inside a clear liquid. The varying densities of the objects caused them to rise or fall depending on changes in temperature. Though a practical telescope had been constructed in the year prior, in 1609 Galileo developed his own, eventually building the model around 30 times magnification. His findings were printed in Venice the following year, giving rise to tremendous speculation and controversy. Galileo supported heliocentrism,
The belief that the Earth and planets revolve around the stationary sun at the center of the solar system. The Catholic Church under Pope Urban VIII thought otherwise and ordered Galileo to stop publication of his findings. Some 6 years later, Galileo defied the Church and published his criticism of Aristotle's perfect universe in his work Dialogue concerning the two chief world systems. Though he was a loyal Catholic, further condemnation by the Church and accusations of heresy forced Galileo to live under house arrest and in isolation. Some of his works were smuggled out of the country and published elsewhere. For his life's work and its influence in the developing world, Galileo has been given many titles, but perhaps the most significant is the father of modern science.
Interesting thing about Galileo. So Galileo was, as it said here, somebody who considered entering the priesthood. He was a very, very devout Catholic. His daughter was a nun. And there's actually a book I've been meaning to read. Jason read it and he loved it. It's called Galileo's Daughter. And basically it is an exchange of letters between Galileo and his daughter. And so it's difficult because his science mind put him at odds with the church, because the church was going with the geocentric model, and that's where the church stood. And he challenged that and got booted, basically. So that was a difficult thing for him. But he was somebody who didn't believe that religion and science had to be at odds. And some people do think they have to be at odds. Yes.
Say, somehow we already thought of that stuff because we found on ancient Egyptian plates, we've seen like images of the solar system.
Yeah.
And it's like, that one's bigger than that one.
Mhm.
That one, and it shows their orbits and where they are.
Right.
We still don't know how they.
Yeah, there are some ancient societies that have, yeah, if you watch, especially if you watch like the Ancient Aliens, dude, woo, like there are all kinds of things that we can't explain that ancient civilizations thought. So Johann Kepler, all right, Kepler was actually the fish I had before this fish. So Kepler here, you can tell by his clothes, he's a very fancy man, fancy boy, very fancy. Now check the date. So around the same time, a little bit later, like I said earlier, a little bit later.
Johannes Kepler was a pioneer in the field of astronomy. He founded the theory of celestial mechanics and was the first astronomer to explain planetary motion. Kepler was born in the Free Imperial City, located near modern-day Stuttgart. He was a very talented child, and his talents led to him becoming a teacher of mathematics in Austria. Kepler was also a great mathematician and physicist, and contributed to theories in geometry and optics. His main body of work was in astronomy and planetary motion, however, and he explained how the tides were influenced by the moon and found the three laws of planetary motion. Kepler was a deeply religious man and credited God with his life and career, as well as for the discoveries he had made. Kepler was of the Lutheran faith, faced prosecution by the Catholic Church. Kepler completed the Rudolphine Tables, a series of star catalogues and books of planetary tables in 1627, and later published astrological predicted calculus due to Kepler's political insights. His main contribution to astronomy was the discovery that the Earth and other planets traveled in an elliptical orbit around the Sun, which changed the face of astronomy forever, as well as our understanding of the structure of the universe.
So here's another guy who is deeply religious. Now he's Lutheran. Sorry, I have a tickle. Why would he be Lutheran in particular? Do you know what about where he lived? Where did he live? Austria. Where are the Lutherans from? Germany, Austria. Okay. He wasn't even Catholic, but the Catholics were like, oh, no, no, no. Right. So they held, I got to get a drink, I have a tickle. They held a lot of power within Europe. Okay. So here's Newton. I'm going to grab a drink. Be right back.
Parish.
Sir Isaac Newton was an English physicist and mathematician, well renowned for his expertise in astronomy, natural philosophy, alchemy, and theology. Much of classical mechanics, or the set of physical laws describing the motion of bodies under force, are laid out in Newton's Mathematical Principles of Natural Philosophy, published in 1687. Newton's three laws of motion are perhaps the most well-known of his works, and cite the following. The first law, or the law of inertia, states that an object at rest will remain at rest, and an object in motion will remain in motion, unless acted upon by an unbalanced force. The second law states that acceleration is produced when an external force acts on a mass. Newton's third law of motion states that for every action, there is an equal and opposite reaction. Newton invented the first reflecting telescope and devised the theory of color. The theory was based on the observation that a prism breaks down white light into many visible colors. Newton is attributed to the development of differential and integral calculus, as well as the generalized binomial theorem. He also developed a method for approximating the roots of a mathematical function. Highly religious man, much of Newton's writings consist of biblical and occult studies. Sir Isaac Newton is considered by many to have one of the greatest scientific minds in our history, and he is buried in Westminster Abbey.
Ta-da. Westminster Abbey.
I said he was buried.
Well, he is buried, but he's not underground. He's like in a crypt.
I believe he also helped found thermodynamics.
He had lots and lots of things. Right? Why did he have to do that?
It's to calculate the slope of a given point.
There you go.
Any point on a-
So hang on. So our present day viewpoints, we have 4 small inner rocky planets, Mercury, Venus, Earth, Mars. Then we have 4 outer gaseous planets, Jupiter, Saturn, Uranus, Neptune. Pluto has been demoted.
Yeah, Pluto. No.
Poor Pluto.
Pluto.
All right, so our inner planets,
Yeah, of the present solar system.
guys, our inner planets. We call these terrestrial planets because they're rocky. First, we have our Mercury. Okay, now this will be interesting. Does anybody know how many moons Mercury has? Caitlin,
4.
but a good guess. All right, look at the temperature on Mercury, by the way, real quick there. Yeah, anybody want to go hang out there? I do not. Why the range? Why the ridiculous range from negative 290 to 800 Fahrenheit, Drew?
The closest to the sun,
That would get it this hot. What gets it this cold?
because there has no sunlight at the back.
Yeah, but the Earth has no sunlight at the back certain times a day. You're close, you're close.
Well, okay, well, because it,
Hang on, Milo.
No atmosphere?
No atmosphere, right? No greenhouse effect, no atmosphere, not much of an atmosphere.
it doesn't stand the sun.
No, it's been pretty bad. The thing is, when the sun is not aimed at it, the dark side of Mercury is gonna have, since it doesn't have the type of atmosphere that Earth has that traps the warmth, it has giant swings in temperature. All right, so here's Venus. Anybody know the length in Earth days of a Venus day? Do you know, Alex? 15, he says. How about 243 Earth days? That's a lot.
Alex, I think you're a little off.
And again, no moons. Okay, here's Earth. What's our radius? Anybody? Hey, Piper?
6,300.
75?
71. She's got it. That a girl. Yeah, a little bit. 6,371 kilometers is the radius.
I believe it's like 0.6.
All right, then we have Mars. Dun, dun, dun. How many moons does Mars have? Oh, use it.
2.
2
Yeah, I
Who?
can name them.
is correct. All right, we don't need to name them. Then we have our outer planets, right? We got to get past our asteroid belt to get to our outer planets. Now, gas giants is probably your most common name for them, but they are also called ice giants and Jovian planets. You'll hear all of these named before. Okay, what's the length of Jupiter days in Earth hours?
Oh.
Anybody want to guess? Yes.
In hour.
I think hours is correct. Maybe it's written wrong, but I'm pretty sure it's hours.
2000.
2000? 9.93. Good guess though. All right, how about Saturn? How many moons does Saturn have? Liam?
Like 20 something?
Like 20 something?
Ooh, not sure.
82. 82 satellites whipping around that thing, plus this whole ring of debris that hasn't concentrated into any particular satellite.
Wait, just a ring count?
No, Alex, did you have the
If
question?
you remember correctly, some of it's stuff in solar like Jupiter.
Oh, that's possible.
Jupiter's
And then we have
so big.
Uranus.
Oh,
Uranus. And what is the year length in Earth years, Yusuf? 84, but a good guess. All right, Neptune. Parker, you guessed what? Where'd it go? Did I miss it? Where did Neptune go? Uh-oh. Did it get out of order? Oh, no. Forget it. It's here somewhere.
Cut.
Neptune's been cut. I don't know where it went. That's really strange. Well, welcome. Neptune, whatever. All right, Parker, I'll give you a different one. Other objects in our solar system. So we have these blank planets, spherical objects that orbit the sun. They're not a satellite. Pluto is now one of these. Parker, do you know what they are?
Free planet.
No. Do you know what they are? Take a guess. Snow White hung out with some.
Yes.
What's Snow White hang out with? Seven what? You got dwarfs. All right, good job.
Dwarf planet.
7 dwarfs, so dwarf planets, all right? Shh. An example would be Pluto, poor Pluto. All right, then we have smaller bodies, our asteroids. We have interplanetary material that's entered Earth's atmosphere. Oh, we've heard this before. What is this one?
Meteoroids?
Entered there you go, meteoroid. So then what's this next one then? A lighted object streaking through the sky. Lily, a meteor, it hasn't hit the ground. It's a meteor. And then what is it when it hits the ground, Liam?
Meteorite.
It's a meteorite when it hits the ground. We know this, right? We've been through these. All right. Then we have the Kuiper belt, small bodies of ice and rock that lie outside of what? Ooh, James.
Outside of the terrestrial.
Neptune, all the way outside Neptune's orbit. Okay, Kuiper belt. And then we have small icy bodies that have highly eccentric orbits around the sun. What would this be? Okay, Milo. Not asteroids, comets. What's a great, easy way to describe a comet? Anybody know?
Dirty snowball.
That's it, dirty snowball. It's a dirty snowball flying through space. It has a head, it has a tail. Periodic comets. Oh, there you go. Periodic comets return. When I was a kid, the big one was Halley's Comet. It came through one year when I was in elementary school. And you know, when they take the school pictures, you see, I mean, you're not in schools, but you see the school pictures people take, it's like a background, you smile. That year, it was a background with the comet. And we all posed with the comet picture. All of us with our bad 80s hair, all of us posed with the comet because it was a big deal. Has anybody heard of the Hale-Bopp comet?
Yes.
What?
And what weirdness occurred with the Hale-Bopp comet? If you want to look up, if you're into weird historical events, look up Hale-Bopp comet. There was a cult who believed they were going to go away on the comet, take a ride. They all wore the same shoes, and they all simultaneously committed suicide and covered themselves with little white. And when the police go in, there's little white sheets and all the same shoes sticking out. It was weird beyond weird. It was a cult thing, Hale-Bopp comet. Yeah, they were oh gosh, I can't remember the name of the cult. The cult had a name though, and it was weird. And there was a very strange guy who led the cult.
I would have joined it.
And he was like, hang on, I'll tell you. The guy was Heaven's Gate. That was the name of it. Oh, and here's the dude. The dude was like this real creepy looking guy. And he had all these videos. This guy, this creepy looking guy. Okay, he led them. It was crazy. This guy.
Ooh.
Oh, yeah. And then he was crazier looking when he had hair. He was better bald. So anyway, yes, ma'am.
The one like poison the Kool-Aid.
No.
That's Jonestown. But these guys did something. Yeah, that was Jones. They did something similar. Yeah, they knew they were doing it. Yeah. All right, so moving on. Now we're going to have fun. All of these planets have symbols. Some of them you might recognize and go, aha, okay, I know what that is. Especially these two. These two are pretty easy because what symbol is this? Yeah, what's this one? Female and this one's male. There was actually a book a couple of years ago well, probably more like 20 years ago now. It was a book about, guys, it was a book about relationships, and it was called Men Are From Mars, Women Are From Venus. So anyway, what's this one? Anybody want to guess?
I'd say Pluto.
Caitlin, what do you think? Neptune. Why would you guess Neptune? It's a great guess. Because it's on your chart.
It also looks like a trident.
It looks like a trident, doesn't it? That would be Neptune. All right, how about this one? All right, James, you go. You're gonna guess Venus, and you're gonna guess right. That would be Venus. All right, so how about this next one? I kind of gave it away for you. Thanks, fun. Oh, well, if everybody's gonna say it, then I'm not gonna let anybody win it. Okay. All right, so what's this one? Anybody want to guess this one? Oh, Jack, what is it? What you guess? What is it? What do you think? Take a guess.
Take a guess.
Pluto. Good guess. That's gonna be Earth. Interesting, right? Okay.
Upside down.
Now this one looks a little like Venus, but not really. So what is this one, Liam?
Mercury.
Mercury. All right, and you're right. Very good. And how about the one that looks like a weird number 2 and number 4? Piper? Jupiter. Very good. All right, and how about the pointy one? Yusuf? Well, Mercury, Venus, Earth, Mars. We don't have Saturn or Uranus. Saturn. Okay, that's a really good guess because it looks like there's a center and an orbit, right? But that one's Uranus. So Chloe, what's our last one? There we go. All right.
Pluto needs a symbol.
So here's our size comparison again. Guys, we just saw this outside, right? One thing we didn't, Liam, one thing we didn't really see when you guys did like the radius and the scaled size of Saturn, look at how big the rings are in comparison. Like we really didn't get that in there, but still pretty cool. All right, so this is a quick one too, but let's show it. Well,
Our solar system is one of over 500 known solar systems in the entire Milky Way galaxy. The solar system came into being about 4.5 billion years ago when a cloud of interstellar gas and dust collapsed, resulting in a solar nebula, a swirling disk of material that collided to form the solar system. The solar system is located in the Milky Way's Orion star cluster. Only 15% of stars in the galaxy host planetary systems, and one of those stars is our own sun. Revolving around the sun are 8 planets. The planets are divided into 3 categories based on their composition:
y'all,
terrestrial and glacial. Terrestrial planets, including Mercury, Venus, Earth, and Mars, are primarily made of rocky material. Surfaces are solid. They don't have ring systems. They have very few or no moons, and they are relatively small. The smallest and closest to the sun is Mercury, which has the shortest orbit in the solar system at about 3 Earth months. Venus is the hottest planet, with temperatures of up to 867 degrees Fahrenheit due to an atmosphere of carbon dioxide and expansive lava flows. Next to this world of fire is a world of water, Earth. The water systems on this planet help create the only known environment in the universe capable of sustaining life. Last of the terrestrial planets, Mars, might have also supported life about 3.7 billion years ago, where the planet had a watery surface and moist atmosphere. Beyond the 4 terrestrial planets of the inner solar system lie the Jovian planets of the outer solar system. The Jovian planets include gas giants Jupiter and Saturn, and ice giants Uranus and Neptune. The gas giants are predominantly made of helium and hydrogen, and the ice giants also contain rock, ice, and a liquid mixture of water, methane, and ammonia. All 4 Jovian planets have multiple moons or rings.
no, come on.
At have no solid surface and are immense. The largest Jovian is also the largest planet in the solar system, Jupiter. Nearby is Saturn, the solar system's second largest planet. Its signature rings are wide enough to fit between Earth and the Moon, but are barely a kilometer thick. Past Saturn are the ice giants Uranus and Neptune. The slightly bigger of these ice giants, Uranus, is famous for rotating on its side.
Y'all, goodness sakes.
Next to Uranus is Neptune, that outermost planet in the solar system and also one of the coolest. Orbiting its terrestrial planets is the asteroid belt, a flat disk of rocky objects full of remnants from the solar system's formation, from microscopic dust particles to the largest known object, the dwarf planet Ceres. Another disk of space debris lies much further out and orbits the Jovian planets, the icy Kuiper Belt. Apart from asteroids, the Kuiper Belt is also home to dwarf planets such as Pluto and is the birthplace of many comets. Beyond the Kuiper Belt is the Oort cloud, a vast spherical collection of icy debris. It is considered the edge of the solar system, since that is where the gravitational and physical influences of the sun end. Our solar system's particular configuration of planets and other celestial objects, all revolving around a light-giving star, make it a special place to call home.
So you saw that image of the Milky Way, right? And then there we were in the middle of it, right? Oh, here's us over here in this one little arm. When you realize that you're only part of this tiny thing, which is part of another small thing, which is part of an even bigger and bigger and bigger thing, it's kind of incomprehensible, right?
We're meaningless specks in the universe.
Yep.
Mhm.
Going down a house.
So the sun, our sun. So our sun isn't even that big of a star. It's not even that impressive of a star. But as far as we know, we're in the only solar system that can support life, and Earth is the only planet that can support life. So here's some stuff. Let's see what we can figure out about the sun. What do we know? So properties of the sun. So the largest object in the solar system contains 99% of the mass in the whole solar system. So everything else we know, and all the other planets are less than 1% of the whole mass, because the sun has 99% of it. So what do we call the visible surface? Caitlin, there you go, your photosphere. If you break that down, what does it mean? Photosphere. Bailey. Yeah, light bulb.
Ball of
Blah,
light.
blah, light. You got it. You got it. Always break down these Greek and Latin terms. Always. All right. So the next layer of the atmosphere is what, Yusuf? Chromosphere. Okay. Chromo. Anybody know that one?
Color.
Mhm. Yeah, color is where we're going with that. Yeah. So it appears red. So there's your color. And the outermost layer of the atmosphere is, Liam? Corona. Yeah, there you go. Crown. She's got it. Yeah, crown. And then what is formed as gases in the corona speed away from the atmosphere? Wait, what do we call that, Chloe? Yeah, you got solar wind. Okay, so think back to when we did our documentaries. All right, and we talked about the sun being more active and there being more flares like this, and that this might be what's causing some of the warming that we experience. Keep that in mind, because this is what we're talking about, this sort of activity here. So this is the activity, and this little guy will play here, and you can see, you can watch this. It's just video. Pretty cool. So what creates pressure that counteracts? Oh wait, it's gonna talk. I forgot it's talking.
Magnetically driven star, but we can't actually see magnetic field lines. They're essentially invisible, and so we have to turn to models.
Parker, are you paying attention?
The global
There you go.
magnetic structure.
Piper, leave him alone.
of the sun. What we're looking at here is one such model, and the color coding represents what we call open magnetic field lines. run all the way out to really, really far out in space.
So let me ask you this while you're looking at that. What would cause magnetic activity? James? What do you think? Polarized particles, you are nailing it. Okay, so we have hydrogen and helium activity in the sun. That's basically what you've got. Okay, 2 hydrogens are coming together, becoming heliums. And that means that we have some free electrons, right? Obviously, if things are joining together, if you've got chemical reaction, if you've got compounds being created or new elements being created, it's because you've got some electrons that can interact. Charges on electron is what? People, all you people, negative, right? Okay, so when you start having those types of electrical stuff, then you get magnetic stuff. That's how we have this whole electromagnetic situation, which we're going to go over in just a minute. So what creates the pressure that counteracts the pressure of the hot gas? What's that one, Liam?
The magnetic field.
Yep, there you go. And where did it? Where are you, Liam? I keep losing you. All right, there you go. And then what are the cooler spots on the sun's surface called, Milo? Those are our sunspots. Very good. And then, oh, stop talking to me. There we go. And then what happens? The sunspots change regularly in the greatest number every 11.2 years when the sun switches polarity. Chloe. Okay, there we go. So, whoop, that one. Solar activity cycle. So the sun is switching polarity every 11.2 years. Does Earth switch polarity? Everybody. Yes. How do we know, everybody? Because there's where do we see the evidence that the Earth switches polarity?
In the ocean.
Ocean floor. Which ocean? Which ocean?
All
Because what kind of plate boundary is there?
divergent.
Divergent. You guys are good. All right. So the sun has some other features. Low density areas located over the sunspots are what, Yusuf? Coronal holes. And what are the violent eruptions of particles flying all over Liam?
Solar flares.
There you go, solar flares. And then lastly, what is this arc of gas that erupts? Piper? Nope, change your mind. Yusuf? Prominence. All right, great. So this video, oh gosh, can't see half of it. I'm going to leave it for you guys to watch because I'm watching our time. We may come back to it, but it's a video that NASA has gotten where you can actually see some of these plasma bursts off the sun. And this one was on May 27, 2014. I think
there's
it's,
a brownie point.
well, the whole thing's cut off right here. It's
Oh,
just
yeah.
not, yeah, the video. How long is the video? I think it's, oh, it's 2 minutes. You can watch it. It's really cool. Yeah. Ding. Here, you can watch it. Look at that. Oh, did we get another one? We're at 24, I thought. Right. Where's it? Oh, no, because the 20, I said, when did I say 24? In the email, yes, you got us to 24, I thought.
You wanted the music?
Ah, so are we at 25? Ah, okay, so then you guys will get some brownies. So solar interior, we're gonna whip through the rest of this sun stuff. I'm watching our time. So energy production. Okay, now, this is not gravitational contraction, but rather the combination of lightweight atomic nuclei. Liam,
Fusion.
this is fusion. This is not gravitational contraction. Know the difference, people. And then what's it called when they split apart, Jack? Fission. Okay. I'm going to leave this one for you to watch, but it will show you fission, fusion, how things go. Okay. And then real quick, just have a look. Here's a good diagram. You can see it's like a cross section. Yep. Cross section of the sun. You've got convection in the sun too, just like we have here, but there it's on the surface of the sun. And then in here, you've got all this energy. And what the energy is being generated by what? What's the process that is creating the energy?
Fusion.
Mhm.
Fusion. And a little bit of fission.
Fission, giving off energy in the form of heat and light, right? All right, now, spectra. This is rainbow, visible spectrum. And we have an emission spectrum. Visible spectrum is produced by glowing liquid or solid or compressed glowing gas. Okay, what is this right here? What's this thing? Who knows what this is? Oh, let's see, Liam.
Prism?
It is a prism. Where else have we seen this? James? Oh, say it again, James.
Dark side of the moon.
Lloyd, dark side of the moon, used Newton's little deal there, right? Goes like this. You know this one? There we are. Yep. All right. So this gentleman shows you the absorption and how this whole emission spectrum functions, because it gets a little complex. This is next year's stuff for real.
Remember, I told you that the first model will be atom is decaying, it'll give out radiation having multiple frequencies, but these frequencies will be continuous. But I told you that's not the case. Now let me come to what I meant exactly. We know that if I heat an object, it is going to give out some kind of radiation, right? Like a flame, for example, or a piece of hot metal. Now, if I take this hot metal, so let me take an incandescent light bulb, which is basically nothing but a heated tungsten film, right? And that's giving out some radiation in the form of light. If I take this light, pass it through a prism, and I keep a screen behind me, what will I get? I get a continuous set of colors, right? Or a continuous spectrum, correct? Something like this. Now, if I change the source to a fluorescent lamp or a mercury vapor lamp, and then perform the same experiment, I find something very different. On the screen, I find only certain wavelengths, with certain colors. But in the previous case, I found a continuous spectrum of wavelengths of color. So, what was the difference? In the first case, I heated a solid, a tungsten filament. In the second case, I was heating a rarefied gas. In the case of a mercury vapor lamp or a fluorescent lamp. So when I heat a rarefied gas, I get only a set of wavelengths on my screen. And this spectrum, this is called the emission line spectrum. And these lines are called spectral lines. We've also found that this set of spectral lines was characteristic for a particular element. Or in other words, an element always produced the same set of spectral lines. Also, it is found that when white light was shined through this element, the spectrum that was observed did not have a few frequencies, or there were a few dark lines. And these dark lines corresponded exactly with the spectral lines that we saw in the previous case. This basically means when a gas emits some radiation, it emits only a few frequencies. And when light is passed through a gas and it absorbs some radiation, it again absorbs only a few frequencies and exactly the same frequencies that it emitted in the previous case. And the second spectrum, the spectrum which we observe when light is absorbed, this spectrum is called the absorption spectrum.
So, if you, has anybody ever heard of a spectrometer? Yeah, okay, so there's gas spectrometers and it's a really cool thing. Basically, like a big old box, but it's a machine, okay? And you have a little syringe with some unknown compound in it. And you can stick it in, like there's a little, like a diaphragm that you can stick the needle into and push the plunger, and the machine uses that spectrum to analyze the exact elements that are present. And it can tell you how much of those elements are present. Now, who was with me for chemistry when we threw chemicals on fires and saw all the, okay. Like what's the main visible light emitted with copper? Like, what do you get? Who knows, Lily? Yeah, it's like a blue green. It's really pretty. And how about, do you remember, anybody remember like strontium? Do you remember? It was the red one, right? Yeah, it's really a cool thing. So when we get back to chemistry in 2 years, That's a fun thing to do. There's a lot about this stuff next year, in physical science. So we'll be talking a lot about spectrum and all that kind of business, and it's fun. It's actually fun. Some of the labs are really cool. So the sun consists of what in 73.4% and what in about 25%. These are our two elements. What's going where? All right. James, which is which? There you go. Hydrogen and helium. That is correct. Okay. So we have more hydrogen than we have helium. And then the composition is similar to that of your gas giants. And the sun's composition represents that of the whole galaxy. Most common element in the universe is hydrogen. Very good. All right. So how do we measure stars? They're so far away. Okay. So now we've got this information, right? We know about what's emitted and what's absorbed. So we have groups of stars, and these are, what do we call these figures or these drawings formed by stars at night? Oh, Parker, you know this. If you look up at the night sky, the stars form shapes, and what do we call that? Like Orion and the Big Dipper. Starts with a C. Hang on. Constellations. All right, great. Now, these are fun. Some are quite pretty. Way to go, Parker. All right. They're visible throughout the year, others only at certain times of the year. Like Drew said, you could tell the sky was apparently wrong in Titanic because you know where to find what constellation when. Some of them I see and I'm like, oh, I get it. Others I'm like, I don't know how you get that. But when you get your Star Walk app, you can take it outside at night, go like this, and it'll say, here's Pisces, and it'll highlight each star and outline the image for you. So you can see it, and it's really, really cool. Okay, so we have a few stars that are gravitationally bound. They appear closer together. Okay, Caitlin, you go. Close, yeah. So I'm going for clusters, but that's good enough. And then when you have two that are gravitationally bound and they circle around each other, Chloe, what's that?
So I know it starts with 5.
Yeah. It's close. Binaries. Yep, there you go. All right, so they're binaries. Now, if you are looking up at the stars at night and you see one that's like really twinkling kind of in a pattern, sometimes that's actually a binary system. And what you're seeing is the rotation, and it's just kind of, it's interesting. You can see a little better that way. All right, so spectral lines shift as stars approach and move away. Liam, what's this about?
Doppler effect.
This is Doppler effect. Okay, this is super important to understand. This applies to not just earth science. It's going to apply to physical science. It applies to lots and lots and lots of things. Your homework will maybe focus around something like this, and it'll be something to think about. Yes, what are you going to say?
Well, it applies to any wave.
Anyway, yep.
When the origin of the wave gets closer, it's gonna cause the frequency to increase, which is gonna change either the pitch or the,
Right.
or what it looks like, or things like that, depending on
Mhm.
which wave. it is.
So here's Doppler effect.
Most people have had the experience of hearing the pitch of a car horn, train whistle, or ambulance siren drop off as the source moves past. As the sound source moves towards the observer, the sound waves are compressed, making the pitch of the sound higher. As the sound source moves away from the observer, the sound waves are stretched out, making the pitch of the sound lower. Same effect works for light. Here we have the visible spectrum of the star. Hydrogen in the star's atmosphere creates absorption lines with a unique pattern. Here's the pattern for a star at rest with respect to the observer. Light from an approaching star has its wavelengths shortened. We see that the lines shift to the blue. They are said to be blue shifted. And light from a receding star has its wavelengths lengthened. we see the lines shift to the red. They are said to be redshifted. The key to measuring the Doppler effect is to measure the change in position of the spectral lines. The further the shift, the faster the radial velocity. With this Doppler effect, we can determine three important things about stars and the gases surrounding them. We can determine how fast stars and star material are moving towards or away from us. We can detect and measure the orbital motion of binary stars. And we can even determine how fast a star is rotating.
So remember we talked red shift, blue shift before? Who was the guy that had all the red shift, blue shift conversation? Who was this person that basically used that information? You know?
Hubble.
Hubble. Okay, Hubble is your red shift, blue shift guy. When you're talking about astronomy, how far, yeah, there you go. Red, one fish, two fish, red fish, blue shift. Yeah, there you go. So stellar positions and distances. The distance light travels in a year is called and yeah, that one's pretty much a given. All right, and it's a little sticking out, but 8.26 light years is, yes, Liam?
Parsec.
Yep, very good. And then the shift in position caused by the motion of the observer is what? Oh, 3, sorry, I read it wrong. I thought it was an 8. Yeah, because it was half covered. Shift in position caused by the motion of the observer is, go ahead, say it.
Parallax.
There you go, parallax. And that is, again, this is the same concept as Doppler. It's this is caused by the motion of the observer versus the other one caused by the motion of what is being observed. So then we have magnitude. I'm just going to whip through these. How bright a star appears is its apparent magnitude because it's how it appears. How bright it would appear if it was placed at 10 parsec is absolute magnitude. And then your energy output is its luminosity. Okay. Now, how do we measure them? How do we classify them? Classification of stars. Okay, here are spectral types. This is based on the color and the temperature in what? What are we measuring it in? Jack?
Kelvin.
Kelvin. All right. And then spectral features. And these are things like ionized helium, whether there's metals involved. So temperature, spectral type, composition, nearly all stars have identical composition. Differences in appearance are usually due to temperature. All right, now keep in mind, we have these stars, they're at different temperatures. These blue ones are like super duper hot, right? All right, now, then we get this kind of a thing. Okay, so this is an HR diagram. It's a Hertzsprung-Russell diagram. So these dudes came up with this idea to put stars in a sequence. And they said 90% of all stars are going to fall right here in its main sequence, this part of the diagram. This is where most of them are going to fit. You got red giants, you got white dwarfs, and these occupy the corners. And then you also have like your blue giants up here. And this is basically just a way to say, where do most stars fit? Oh, let's make a graphic. Why not? Alrighty. So how do stars evolve? They don't stay the same, clearly. So your basic structure of stars, mass effects, the bigger, the greater the gravity, the hotter and denser. So the bigger star is going to be hotter, denser, have greater gravity. Then you have fusion going on. Stars in the main sequence produce energy. That's that diagonal, right? By fusing hydrogen to helium. And stars not on the main sequence fuse other elements, or they don't undergo fusion at all. By the way, that little thing was called the Horsehead Nebula. I'm going to skip that because I'm watching our time. There were lots of videos for this because it just kind of helped. All right, you've got this diagram. Let's do them together. You have the diagram in your notes? So number 1 is what? Just say it together. Nobody's going to say it. That's your nebula. What's number 2? Say it. Just say it out loud if you've got it. Just your main sequence star. What's 3? Red giant or supergiant in this case. What's 4?
Big boom.
Supernova, kaboom. What's this one? Number 5.
Not quite a black hole.
Yep, that's here. And
That's
this one. So you have a neutron star. I don't know why this is over here twice. I should have said 6. Okay, 6. What happens here? There's your black dwarf and your black hole. And then what's 7
Red dwarf.
Red dwarf.
and 8?
Planetary nebula,
Planetary nebula. 9
white dwarf.
white dwarf, and then 10.
Black.
All right, little itty thing. There you go. Now, this is the last thing I have to show you today, or second to last thing I have to show you today. Beetlejuice. Okay, this is one of these ones, you can look it up. Guys, you can look it up. There is a lot of discussion about the pronunciation. Beetlejuice, Beetlegeist, Betelgeuse. There's a bunch of them.
Beetlejuice.
You most commonly, guys, you most commonly hear Beetlejuice or Beetlegeist. This was just, hold on one second. What was this last page? Hang on. Oh, the Carl Sagan quote. Okay. I had to do this. You'll see why. But my point is that Beetlejuice will supernova. It's going to happen soon. We don't know what soon means. Soon could be tomorrow. Soon could be 10 years from now. But it is approaching supernova. It's a red giant. Yeah, maybe. We do know there were some very large flares within the last year that made scientists start to worry. So anyway, this was necessary.
I am Beetlejuice, I'm your age, the hand of the hot and brightest of the window, night sky. And the red super dot, and they come to explode, to the supernova in all. And take it over, see the naked creatures, such type of donor, an astronomer and a great scientist. On the second brightest star in the oscillation, after the star Roger, risking from any of its stations. My diameter is the bus and I'm not that I have you done. And 640 lectures of the earth is wide open. The surface temperature is 67 degrees. And you're some sort of method of the place of that drag. So massive if you read this, you're done with me. I've reached past the orbit of Jupiter. I'm done. See, I consider they have started to spend million years so to explode into its supernova scientists. I am Beetlejuice of your age, the end of my life. It's hot and bright, it's stuff the wind. It's Beetlejuice, dying, expected to explode by the fingers to in like 100,000 years. Super giant is an aging giant star that has consumed its course of diet. That's what they are. Purely accumulated microscopic well and hydrogen's undergo in my outer shell. When my outer shell's expand, I think on a red color because it's over that what I'm happy to discover. The super giants on those large the universe, and I'm expected to supernova onto the next first. Serving fusion heavy ones are created until my forest. And that's when I'm out of good without even trying. I happen to the star and passing that me the entire all that's the same excludes the paper you see. When I do supernova, forget how to sight. Somebody can't even look like you're bright. It's like the radiation I put up on becoming a supernova wouldn't affect her because of 640 light years old. And you'll choose something.
Yeah. So Beetlejuice will supernova. It's getting closer and closer. Will we be able to see it? Quite possibly. Is it going to affect us?
Probably not.
No,
Let's hope.
because it's over 600 million light years away. It's not going to affect us, but we've already seen some of the activity on it that's making us nervous that it's going to go. Now, I'll tell you this, just so you know, if you go to YouTube and you write and you type in, Beetlejuice going supernova, you'll see 100 people who have videos that say, live happening now. It's happening. It's not happening. It's not happening. They've really, some of these guys have really marketed it like we're watching it now and you're missing out. Breaking news, some of them say, not breaking. We've known this for a while, but you can find some articles, some images from, I think it was August and October of this last year, where you find a lot of activity. Yes, Yusuf. Well, it's gonna go supernova and then what?
We're doomed. Basically.
We're not, whatever happens to it, it's not gonna affect us. So who's Carl Sagan?
The guy who said that.
Anybody know who Carl Sagan is?
Heard the name.
Carl Sagan's an author, okay? He wrote, like, for example, Contact. Anybody seen the movie Contact or read the book? I highly recommend Contact. If you want to watch a really good movie, that's a really good movie. It's Jodie Foster, I think Matthew McConaughey. Anyway, this is a Carl Sagan quote that I wanted to end this lesson with because it's really good.
We are starstruck.
The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in interiors of collapsing stars. We are made of star stuff. We are star stuff, which has taken its destiny into its own hands. That's a cool quote. We are star stuff. So y'all, the answers to your notes are in here. Now, next week, listen, next week is the last lesson. Then we review for final. Let's try next week to keep the back and forth chatter to a minimum. Okay, that sucked up some time today and we didn't get through like all the video. I don't want to show too many videos usually, but some of them were too good. Now, wait. I'm going to turn this around to get your money, but on the counter, I have a bunch of little space stickers. You can each take 2 if you want them. Some of them are cool.
Yeah. Because you're not getting a point. Read my card. Talking about stuff being attracted by cardio. What?
All right.
Yeah, we saw every coins. No, first year I took it. Oh, you lost my privilege. Beep, beep, out of my way. Oh, I got a lot.
Don't eat things.
I think it was just some popcorn.
Eat that. That's not good fun. Oh, it's not good fun.
It's like sometimes my dog just gives us kids to like bribe us into not making her own trouble.
Use that. Those are for you. Those are for you.
Bye, Dennis.
Bye, sweetie. Have a really good trip. We'll see you in the fall. Bye, Yusuf. Enjoy. See you. Yes, you will. You'll see your cousins and your grandma.
Just so I can brag.
You're such a good boy. No. This is my friend. Oh my goodness, he's so little.
Doesn't matter.
People's coins.
Hey, Parker, you're gonna use your coins.
Yeah, there's
Oh.
Over there. You guys, fill it up. Every week. Still more and more, and before I know it, it's all full. That is not good. now that is the whole right? You change your business model. And that is what like in general, is an issue. So what do you do? But if you do change the business model, it might record. So it's kind of very. It's been everywhere. It's been a big thing. But if he accepts it and it's like, yes, it's yours, then that's when the hearing will large. Politically correct thing to do, what's more popular thing to do. But it can wreck. Right, like that's. Yeah. Anyway, like it can be getting off gender, what is it more? In this case, yeah. Yeah. It can change, but you could. I heard about it. I'm cheating on it. I heard about it. I'm very curious. One of the standardized tests. Right now, we look of the impacts of COVID. So now the schools are taking this. It's gonna matter. So, yeah. Dachshunds are scent hounds, meaning they hunt by nose. There are scent hounds and sight hounds. Dachshunds are scent hounds. Oh, geez, still going.